G'day. This time we're going to consider integrating functions to a given power rather than just x to some power. This complicates matters a little, but again there are two basic methods or two basic patterns to consider. Both of them we derive by looking at the derivative to start with. So let's start at that point. Let's find the derivative of some function to the power n. Using the chain rule, what do we get? Well, when we integrate something to the power n, we get n times the something to the n minus 1, and then we have to multiply by the derivative of what's inside. We multiply both sides by dx. This is working towards our integral now. I'm going to swap these two to bring this derivative forward. I'll explain why in a moment. It's not absolutely necessary, but it's just nice. And again, as in the last time, we integrate both sides. Now the integral of the derivative undo each other because integration is finding the antiderivative. So they undo each other. We're left with some function of x to the power n is the integral of n f dash x fx the n minus 1 dx. And this is the first of our two patterns. I don't have room on the board to show you both patterns at the same time. In fact, I don't even quite have enough room to show you an example. But in the last video I called this a method, so I'll do that. Method number one. Method number one is to try to recognize or build this pattern, which will give us a rather simple result. Now, I may have room just to do a simple one. Let's do something like this. What if I had x You notice this is decidedly more complex than what we had in the previous video. The thing to look for when you see a complicated pattern and a simple pattern multiplied together is to see whether this simple pattern is the derivative of what's inside. To see in fact whether you have the derivative of this function inside the power. Now the derivative of x squared minus 5 is 2x. And the only difference between 2x and that is a constant. And constants we can manipulate with integrals. We can't integrate the actual functions, we can't manipulate the functions themselves greatly. You certainly can't move x values inside and outside an integration. But constants we can. So effectively that is, or at least can be changed into, the derivative of this. So in order to perform this integration using this technique, I'll just grab a red colour here, we just need first of all to have this derivative outside, so we need a 2 here. And to compensate we multiply by 1/2. So 1/2 of 2 is 1, it doesn't change the value. Now that is the derivative of that. If I like, I can write f dash x and fx here. So we've matched that part of the pattern. Now the other part of the pattern is we need a number here which corresponds to this number up here. In fact, it's 1 greater than that. If I add 1 to n minus 1, I'll get n. So to make this follow the same pattern, if I have a 7 here, I also need an 8 here. Multiplying, of course, because these are multiplied. And if I put an 8 here, I have to compensate by multiplying by an 8th on the outside, because 1/8 of 8 is 1, so it still doesn't change the value. So this pattern we have now is, there's our n, is worth, actually I should do that in blue, shouldn't I? I'm losing track of all my colours. Here's blue. There's my n, and there's my n minus 1, my 7. So we've matched this pattern. So in black, we're very close to finishing the integration now. On the outside we have 1/8 of a half. Multiplying these together we get 1 on 16. And then all of this exactly matches that pattern. So the integral is fx to the power n. And n, remember, is the number in blue out the front here. So it'll be fx was x squared minus 5. And it will be to the power 8. Plus c, of course. In the last video I left the constant off when I was first introducing this to concentrate on the process itself, and one of my first comments quite correctly pointed out that it should be there with any indefinite integral, so I should add it in. But there it is. I know it looks awfully complicated, probably more complicated because I've written extra stuff under it, but that's the pattern. I'm going to rub this off and perform a couple more of these kinds of integrations using this pattern, and then I'll show you the second pattern, and you can choose which one you like, or perhaps practice both of them. But let's get on to that now. Well, here we have two functions, the kind of which is, if you're a beginner, if you're learning integration, you certainly don't like to see in school textbooks. They look quite complicated. But I want you to notice this function on the bottom in the denominator can be moved up to the top just by changing the index. Remember, negative indices move functions up and down in fractions. So the fact that it's on the bottom is not that big a deal at this point. The function we have inside, 9 minus x squared, if you take the derivative of it, we get minus 2x. Which is an x function, and we have an x here. So this is a situation where we're going to have the derivative of this function out the front. Notice here, this could just as easily move up by making the index a -4 up here. And here's our function. We're going to have a function of a power to some power. What's the derivative of this function? Well, it's going to be 3x squared plus 3. Now, 3x squared plus 3, we can take 3 out as a common factor. That's a terrible 3. I think I've just messed up everything here. We can take the 3 out as a common factor and get this. And notice, that's exactly what we have on the top. So if you can recognise these, you suddenly realise this is the key to unlock how to integrate these particular functions. Here we have effectively, apart from the constants, we have the derivative of what's in here, and here we have the derivative of what's in here. To make it more obvious, we're going to change everything into index form. So let's do that with each of them. I'm going to leave a gap for my constants. I'm going to write 6x times 9 minus x squared to the power -1/2 dx. This one, I should remove that, but we'll just put a line through so I ignore it. This is the integral. I'm going to leave a gap again for the numbers. X squared plus 1 times x cubed plus 3x to the power -4 dx. Now the first thing we want is the derivative of this out the front. So I'm actually going to move the 6 out of the road. Let's make our adjustments in red. The derivative of 9 minus x squared is minus 2x. So I want a minus 2 sitting there in front of the x. And to compensate for it, I've got to multiply by 1 over minus 2, or minus a half. I'll put the minus 2 on the bottom. Similarly, with this one, the derivative, that looks a bit closer to a 3, the derivative of x cubed plus 3x is 3x squared plus 3, which is 3 lots of x squared plus 1. So I actually need a 3 here, so that that is the derivative of that. To compensate for putting this 3 here, I need to multiply by 1/3 out the front. Because a third times 3 is 1, and multiplying by 1 is not going to change the integral, nor is this product. So now we have the derivative of the function inside. That's the first part of the pattern. The second part is to have a number here which is 1 greater than that. Let's use blue. A half plus 1 is a half. And to compensate for multiplying here by a half, we multiply outside by 2, or 2 over 1. Again, that product is 1, and multiplying by 1 won't ultimately change the value. If we add 1 to this, we get minus 3, and to compensate for that, we multiply by 1 over minus 3. And now we have the exact pattern we had before. You might remember, I won't write it out, but you can look back in the video and see that we had the integral of n f dash x times fx to the n minus 1. And we've followed the exact pattern where this is 1 more than that, and this is the derivative of this. So now we're ready to integrate. Here we have 2 over 2, which will divide out, and we have a negative sign with a 6. And all of this integral here, all of that, becomes this function to that power, plus c, of course. Now, isn't it surprising that all of this reduced so quickly to such a nice little result? Here we have 1 over minus 3 times 1 over 3. 1 times 1 is 1, 3 by 3 is 3, and we have a minus sign which we can sit right out the front. And all of this integral is going to be this function to that power plus c. And that's how that pattern is used to integrate apparently very complicated functions, provided the function on the top or out the front is the derivative of the function inside the power, provided that's the case. What I'm going to do now is show you the second method, which really is not that very different. It just involves moving a constant. And I've seen textbooks that recommend this, and I've seen textbooks that recommend the other. They're both quite valid. But let's get rid of this and go to the next step. For the second method, we start with the same derivative. The derivative of some function to the power n, I've rearranged this into the second form, is n times the function to n minus 1 times its derivative. And I put the derivative in this position. Again, we multiply both sides by dx. And as we did before, we integrate both sides. The integral of the derivative undo each other, and we get this. Which is what we had before for the first method. For this method, we increase the value of n wherever it appears by 1, which makes it still follow the same pattern. So this has been increased by 1, this has been increased by 1, and that's been increased by 1. And because we can move constants, n plus 1 is a constant, because we can move constants inside and outside integral signs, we can actually divide both sides of the equation by this, and we get fx to the n plus 1 over n plus 1, I'll put it in parentheses, equals the integral f dash x fx the n dx. Oh, by the way, we do call this f dash x, but right from the time of Gottfried Leibniz, who invented the terminology, those were Roman numerals, just in case you wanted to know. So the first derivative was the Roman numeral 1, the second was Roman numeral 2, 3, and then IV. They didn't just keep adding strokes. So your eighth derivative would be f v I. Just a little bit of interest. This here is the pattern for our second method. Right, method number 2. Now, what's the difference? Just as in the last video, we had one method where we had a slightly complicated looking integral gave a simple result. Here we have as simple an integral as we can get, giving a slightly more complicated result. Now, we couldn't bring the derivative out of the road as well, because being a function of x, it cannot be removed from the integral. So this has to remain, but we could move the constant. So using this method, you might like to jot it down on paper. I could try and post it over the video while I do the next, but I don't want to clutter the screen. I'm going to perform a couple of integrations using this method. And I have no great favourite. I use both, and it's good to learn both. It's probably better to concentrate on one method or the other if you have a preference. But I'm just going to remove this now and perform 2 more integrations and show you this method in action. Well, here we have 2 integrals. Notice they're fairly nasty looking again, but I want you to see the kind of pattern you're looking for. Here we have a function with a power, and the derivative of this function is 5x to the 4th power, and we have an x to the 4th here. So this, apart from the constants, is the derivative of the function inside. This is the pattern we're looking for. This one here, we have a function with a power. The derivative of this function is minus 3x squared, and we have an x squared out the front. So again, except for the constants, we have the derivative of the function outside of this function to a power. Again, the pattern we're after. Now, what we have to do is massage these into the right sort of pattern. And we'll do them at the same time, so you can see the same operation taking place. First of all, I know that 7's not the number I want, so I'm going to write it out the front, times the integral. I'm going to leave a little bit of a gap for my numbers, and I'm going to write my 7, sorry, oh dear, I've already got rid of the 7, haven't I? I'm going to write my x to the 4th power, and I'm going to move this up as x to the 5th power plus 2 cubed to the power minus 3 dx. I don't know what's wrong with me today, I'm not writing accurately. This one, I'm going to move the 5 out the front, and I'm going to leave the x squared. This one's already in the right format, 8 minus x cubed to the power 6 dx. Just a little bit of a gap so you can separate the minus sign. As I did before, let's do the function in red. The derivative of this is going to be 5x to the 4. So I want a 5 here, which means I multiply by 1/5 out the front, and that compensates. This one, the derivative of this is minus 3x squared, so I want a minus 3 here, and to compensate I multiply by 1 over minus 3 or minus 1/3, whichever. I'll do it this way, whichever you prefer. And for this second method, that's where we stop. We do not try to create this number because it comes out in the integral. So here we have 7 over 5 times, and the integral of this is this function to 1 greater power, increase this by 1, makes it minus 2, and we just put it over minus 2. That's the difference between the two methods. One method, this minus 2 ends up being out here and gives us the integral gives us a more clean result. This integral gives us this result. This one, this would be minus 5 on 3. 5 times 1 is 5. 3 remains on the bottom, and a positive over a negative gives us a negative result. Times, and we're going to get 8 minus x cubed. I'll use parentheses. The vinculum, the bar here, actually performs the same function as parentheses, as a grouping symbol. Add 1 to the power, and we put that same number underneath. Plus a constant, of course, since there are no bounds or no limits on the integral. It's undefined. Now, I don't have room to fit that on, but all we would do is multiply this constant here, so we'd end up with minus 7 on 10, or here we'd get minus 5 on 21 times the function. But that's the second method in action, where we don't worry about matching this up, but the number actually appears down the bottom. The reason I haven't gone into great and terrible depth with this is because I recognise the vast majority of you have learned integration before, and you're watching these videos as a kind of revision. So these are not instructional videos, they're revision videos, and therefore I've taken some liberties and left some things out. I hope that's helped. Please leave your comments, I'd appreciate them. Certainly like the video, and if you're not already a subscriber, I encourage you to subscribe. And thank you very much for watching.